everybody. Welcome back to Intro to Physics. Let's see, this is day 10. I think having off on Monday kind of threw off my count, but I think today is day 10. Yeah, welcome back. We're going to be starting a new topic today, Newton's Laws of Motion, Chapter 4. So most likely, this will be a review of things that you have seen already in school, either in like middle school, just like a brief intro to them in middle school, or of course, if you took physics in high school, any level of physics, you would have seen Newton's laws of motion in physics as well. So today we're going to just run through those 3 laws of motion, just kind of what they say and what they mean. And then starting tomorrow, we'll start applying them in different scenarios and putting them into problems, that sort of thing. So today is really just an overview of what his laws of motion say. So really quickly, just because there are a lot of misconceptions surrounding Newton's laws and how they apply to our everyday life, I have this quick kind of pretest about this, just to check your understanding. So I want you, for each of these 20 statements, I want you to just jot down or make a mental note whether you think the statements are true or false. So again, there are 20 statements. I'll give you a couple of minutes to look through them, and then we'll go through which ones are true and which ones are false. Okay, so take a look at these first 9. Take a couple of minutes to look through them, and then again, we'll move on to the next ones once you have some time to think through these. All right, moving on to the last few statements. Again, write down whether you think these are true or false, and then we'll come through together and talk about them. All right, so hopefully this was a good intro to just kind of get you thinking about how these sorts of concepts apply to our lives. And also these are, I would say these would be pretty great true-false questions that you would see on a quiz. Having been a teacher before, I have asked some of these as true-false questions on quizzes and tests, just to see if students like really understand the physics behind life, or if they just go based off of what they see or what they think or what they've seen in movies, that sort of thing. So let's go through some of these answers together. Boom. 1 through 9, all of them are false, which surprises a lot of people. But as we go through some of these laws, I think you'll see why a lot of these are false. Actually, a lot of these statements are very similar to each other. So, for example, number 1, a force is required to keep an object moving in a given direction, is actually very similar to number 2 and number 3 and number 4 and number 5 and number 6. Like, they're all very similar, just a slightly different application of number 1. So yeah, don't get tripped up by these things. And again, as we go through these laws, we'll talk about why some of these are false. Although I will point out really quickly, number 8, I had a lot of students in both physics and astronomy when I taught astronomy, like honors astronomy, who thought that there was no gravity in space. That seems to be a very big, common misunderstanding of what is happening in space and why astronauts float around. There has to be gravity in space, because if not, there would be nothing keeping the planets in orbit around the sun. We would all just fly off in random directions, and that would be no good. So there has to be gravity in space. That's definitely not the reason why astronauts are floating in the International Space Station. We'll talk about that. Okay, the next couple does have a few true statements. Number 11, an object weighs less on the moon than it does on the Earth. That's true. Weight is another word for the force of gravity, which depends on the acceleration due to gravity And last week we had an example problem of like a rover or something landing down on the moon. And we talked about the acceleration due to gravity on the moon, how that's less than on Earth. So the force of gravity is less on the moon than on Earth, and that's why you can see astronauts bouncing a little bit higher. Number 12, the mass of an object on the moon is the same as its mass on the Earth. That one is true as well, and that I think students oftentimes confuse the ideas of weight and mass, and they are different things in physics. Sometimes in everyday language, we use them kind of interchangeably, like, wow, that thing is so massive, it weighs a lot. Like, okay, yeah, true, they're related to each other, but the mass of an object is just how much stuff it's made out of. And so if you take like a ball, for example, let's say a bowling ball on the Earth, and you take that same bowling ball to the moon, well, it's still made of the same stuff, the same amount of stuff. And so its mass is the same, even though it might weigh less on the moon. Okay. Number 16 was also true. A free falling object still has weight. Again, that comes down to do you know what the word weight actually means? It's a synonym for the force of gravity. And so we talked about last week when an object is in free fall, the only force that we consider acting on the object is the force of gravity pulling it down. So if the force of gravity is present on the object, then it has weight, even if it's, falling through the air. Number 18, a more massive object has more inertia than a less massive object. And as we go through Newton's first law of motion and learn what that inertia means, you'll see that this one is true as well. But all of the other statements are false. So hopefully that opened your eyes to some misconceptions that you might have as well. And hopefully we can dispel some of those misconceptions as we go through his laws. Here we go. So this is another example of misconceptions quiz. If you want to kind of see where you might have misconceptions, check out this link. It's great. Okay, so Sir Isaac Newton, kind of a big deal in physics. He had this quote that I just love. I think this is so interesting. If I have ever made any valuable discoveries, it has been owing more to patient attention than to any other talent. And that just, I mean, just thinking about that is really, really interesting, and kind of encouraging for a normal, like non-Isaac Newton person as well. Because, of course, he made some pretty significant and valuable discoveries. But he says it's not because he was talented, it's because he was observant and patient and attentive. And those are qualities that we can all work on having more of. So here are just some of the valuable discoveries that he has made. So first of all, these three laws of motion that we're going to go through laid the foundation of classical mechanics. So all of physics 1 and beyond that are referred to as Newtonian mechanics because they were all created around these laws of motion, which they're still excellent approximations at these everyday speeds and everyday scales that we deal with in our lives. He was the first to formulate the notion of gravity as a universal force. So gravity isn't just present on the Earth, it's present everywhere in the universe. And so this notion helps to explain tides, which is why you see the ocean in the background in that picture, the trajectories of comets and other, cosmic objects. Of course, later this was superseded by Einstein's theory of general relativity. But again, all of Newton's laws are still excellent approximations for the scales and speeds that we use day to day. A book that he wrote, Principia is the nickname for it, is one of the most important works in the history of science. So this outlined a revolutionary new mathematical description of the universe, which was calculus. So in this book, he explained Newton's laws of Kepler's laws of planetary motion. He validated, kind of proved the heliocentric model of the solar system, saying that the Earth is not at the center, the sun is at the center, and all of the planets are orbiting around the sun, which was fairly revolutionary. Revolutionary. Anyway, it enabled the following industrial revolution. It's the fundamental work for all of modern science, so pretty important. He discovered the generalized binomial theorem in 1665, which is valid for any rational exponent, and it's still used extensively in math today. So if you haven't used it in math yet, you probably will in the future. He invented calculus in 1665. No big deal. Let me just invent calculus. Whatever. He invented the first reflecting telescope in 1668. So previously, telescopes had used lenses instead of mirrors, but lenses are very, very difficult to use just because you have to make sure that both sides of the lens are like super precisely ground and polished and curved to the right curvature. And so these telescopes that use lenses have to be enormous compared to telescopes that use mirrors. So that really revolutionized the field of optics. He determined that white light was a mix of colors that could be separated and then recomposed using prisms, which is like the foundation for physical optics. He identified light as the source of color sensation. So basically saying that color is a result of objects interacting with already colored light, as opposed to objects creating the color themselves. So it's light that gives something the color that we perceive. He inferred the oblateness of Earth's spheroidal figure. So the Earth isn't a perfect sphere, it's kind of squished because it's rotating. He performed the first analytical determination of the speed of sound in air. So these are just a couple of examples of the valuable discoveries that he's made. And again, he says that these discoveries owe more to his patient attention than to any other talent that he possessed. So maybe a motivational moment of the day for you. I don't know. You can do it too. Be the next Isaac Newton. Okay, so into his 3 laws of motion. And we're going to go through them kind of out of order. We're going to do 1, then 3, then 2. I just think it makes a little bit more sense that way. So Newton's first law is also known as the law of inertia. And so the way that we commonly hear this is an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an unbalanced force. But some versions of this law add in this little like middle portion, which I have in bold. It's kind of tough to tell that it's in bold, but in a straight line at a constant speed. That's the kind of motion that it tends to stay in. Stays in motion in a straight line at a constant speed unless it's acted upon by an unbalanced or outside force. So basically, an object's going to keep doing what it's already doing unless something makes that change. And so it'll take a force to make the motion of an object change. So we can see down here this kind of equation for this law. This symbol right here, we may have seen this before in math. This is sigma, capital sigma. It means the sum of the forces. And again, if we remember back to chapter 1, force is a vector, so it's written in this bold italic font, just to show that it is a vector. So the sum of the forces is 0. That means there's nothing unbalanced in the system. Every force is balanced by something. And if that's true, then the change in its motion, right? Whenever we see a derivative or, dv or delta v over delta t, that means a change in the velocity over a change in time. So if there's no unbalanced force, then there's no change in how the object is moving. There's no change in its velocity, either the speed or the direction that it's going. So we really have to understand what is a force in order to make sense of these laws. And so a force is an interaction. Usually we say it's a push or a pull, which could cause a change in the object's motion. Now, it doesn't have to change the object's motion. It could potentially change the motion, right? If that force is unbalanced, then it will. But if it's balanced by something else, then it won't change the object's motion. So there are two different types of forces that we have. There are contact forces, where two objects are actually touching each other. So for example, I have there your foot kicking a ball. That ball is not going to go anywhere until your foot actually hits it, and that is a contact force. The table holding up a textbook, well, the table is pushing up on the textbook. And so that is another example of a contact force, because the book and the table have to be touching each other in order for the book to be supported by the table. There are also field forces, and with these forces, the two objects do not have to touch each other. So that would be gravity, electricity, magnetism. Those are all field forces, because we don't have to be touching the earth to still be influenced by the earth's gravity, right? Whenever we throw a ball up in the air, it's not touching the earth anymore, but it still comes back down because gravity is a field force. It can act at a distance. The earth, it doesn't have to touch things in order to still pull them back down. Same thing with magnetism. If you ever played with magnets before, and you get two magnets that are close together, they don't have to be touching each other to still feel that either attraction or that repulsion between the two magnets. So those are field forces. When we're talking about a force, it has a unit, which of course is named after Isaac Newton. So that's the Newton, and that's the symbol capital N. So, 1 Newton of force would be the amount of force that it takes to accelerate 1 kilogram mass 1 meter per second squared. That's how we define a Newton. So a Newton is also a kilogram meter per second squared. Although that's a mouthful, so we just call it a Newton. Okay, so I have that law up there again in gray at the top. But this law also tells us that only unbalanced forces change the motion of an object. So, for example, if a soccer ball is at rest, it takes the force of a kick to make it move, or the force of wind blowing on it, or something like that. It takes a force to make that soccer ball move from rest. Another example, playing tug of war. Two teams are playing tug of war, and they're pulling with equal force on the rope, but in opposite directions. Well, in this case, neither team is going to go anywhere. They're just going to keep getting more and more tired until one team starts pulling harder than the other. And when they start pulling harder, that means they're applying more force than the other team. And so that little bit of extra force that they're applying to pull is that unbalanced force. So once they create that unbalanced force of pulling harder than the other team, then they'll start winning and gaining some ground in tug of war. So really the key here to this law is changing the motion, right? So an object at rest tends to stay at rest. An object in motion tends to stay in motion unless something makes that change, right? And that's the unbalanced force. So a key thing to keep in mind here then is that an object that is at rest still has forces that are acting on it, right? That soccer ball still has the force of gravity pulling down on it, but it also has the force of the ground holding it up, and those two forces are exactly balanced by each other, right? If they weren't balanced, if the force of gravity were bigger than the normal force, then that ball would fall right through the earth. And if the normal force were bigger than the force of gravity, then it would be like the ground is launching it up into the air. Neither of those things are happening if the ball is at rest. So that means those two forces are balanced, right? Even though it's at rest, the soccer ball still has forces acting on it. Same thing with the tug of war. If you guys are pulling at the same force, you're still pulling, right? You're still applying a force. It's just you're not moving anywhere unless it's an unbalanced force. Okay, so keep that in mind. So again, this law is often called the law of inertia. And inertia is one of those vocab words that you'll want to remember. It's the tendency of an object to resist changing its motion. Now, it's not the tendency to resist motion. It's the tendency to resist changing its motion. Changing is, again, the key word here. Inertia is not a force. It's a tendency of an object. Just like you're laying down on a Saturday morning, it's like 5 in the morning, and then your brother comes in and says, "Hey, let's go for a run." I mean, I hate running. Like, that's the worst punishment somebody could do to me, is to wake me up at 5 in the morning and make me go running. So I would have a natural tendency to resist changing my state of laying in bed, right? That would be like an emotional inertia. So it's not a force, it's just a tendency that objects have to resist changing their motion. And all objects have inertia. The more mass they have, the more inertia they have. So it's harder to change the motion of an object that has more mass. Right? So for example, let's say there's a train just like sitting on the tracks and you're going to try to push it and make it start moving. Good luck to you. It's really hard to make a train start moving. But once it is moving, it's hard to make it stop moving. Right? It's tough. So another example, on your way to school, a bug flies into your windshield. And this happens a lot in Florida. We get a lot of bugs. So since the bug is smaller than your car, less mass, it has less inertia than your car. And so its motion is easier to change than your car's motion. So the bug will more likely splat on your windshield than make your car come to a screeching halt. Right? Your car has more inertia, it has more of a tendency to resist changing its motion than the bug does, unfortunately for the bug. So if objects in motion tend to stay in motion, why don't moving objects keep moving forever? That's the big question here. And really, that's because there's almost always an unbalanced force that's acting on the object. Friction, for example, if an object is sliding, then there's definitely friction between the object and the floor, which we'll talk about later on. But that would be an unbalanced force. Gravity can sometimes be an unbalanced force as well, right? If we're thinking about throwing a ball up in the air, it doesn't keep on going up and up and up forever, right? Gravity is an unbalanced force, so eventually gravity is going to be pulling it back down. Air resistance can be another unbalanced force that usually we do not consider in problems, just because it makes the math a lot more complicated. But there might be times where you do have to consider air resistance, and that would be an unbalanced force. So a book sliding across a table slows down because of friction. Sorry, that should say a ball thrown upwards slows down and falls back down because of gravity. And then in outer space, away from friction and other objects, a rocket ship that is launched with a certain direction and a certain speed would keep going like that forever, in theory. There's no air to slow it down. There's really no like surrounding molecules to create friction on this rocket. If it's away from objects, then we're away from these large sources of gravity. So in theory, it would keep going in that same direction at that same speed forever until it, hits something or gets too close to a planet or what have you. All right, so Newton's third law is also known as the law of action-reaction. So the way that we often hear this is, for every action, there's an equal and opposite reaction. And I've found, teaching physics, that this law is very often misunderstood by high school students. And so I added in force in parentheses in there. So for every action force, there is an equal and opposite reaction force. And that's because the most common misunderstanding of this law is that a reaction is a result. So like for every action, there's a result. For every book that I push off a table, it will fall down to the floor. That's not what this law is saying. A reaction is not a result. A reaction is a type of force. And so this is the way we see it written mathematically. The force of object A on object B is the opposite of the force of object B on object A. So they're equal to each other in magnitude, but they're opposite to each other in direction. Okay. Sherry, you did not miss the second law. We're going to come back to that one after the third law. Okay. So a force, remember, is a vector. The direction makes a difference. And so since any object can have multiple forces acting on it at once, each force, each action force would have a reaction force as well. So here are some examples of what I mean by this. Okay, if you guys watch The Office, this is for you. So Andy gets angry and punches a wall. Okay, here's our nice little clip of that. Not wise, Andy. So here, the action force, well, I guess the interaction pair, the two objects that are interacting in this are Andy's hand and the wall. The action force in that interaction pair is Andy's hand hitting the wall. The reaction force is the wall hitting his hand back. Right? They hit with equal forces, which is why it hurts your hand if you punch a wall. If the wall weren't hitting you back, it wouldn't hurt your hand. And so the result of this is terrible pain, a hole in the wall, and Andy has to go to anger management. Right, so can we see here the difference between a reaction force and a result? Right, the action force is his hand hitting the wall. The reaction force is the wall hitting his hand. Same magnitude, opposite directions, right? Because his hand is going this way, the wall is kind of pushing back on his hand this way. And now the wall gets broken because it can't withstand that force that's being applied to it, but it does momentarily give that same magnitude as a reaction force. Okay, so the stronger the action force is, the equally strong the reaction force will be. They are equal in magnitude, opposite in direction. So here's another example. Dwight is sitting on his fitness orb. Okay, so here, in this clip, you can see several different interaction pairs or pairs of objects that are interacting. But here, in this scenario, we're going to focus just on Dwight and his fitness orb. So the interaction pair is Dwight and his orb. The action force is that his body is pushing down on the orb, and the reaction force is that the orb is pushing up on his body. So he doesn't go anywhere because those two forces are equal to each other and opposite in direction. They're balanced by each other, right? So his body's pushing down, the orb is pushing up on his body. That's the action force and the reaction force. And the result is that Dwight can sit there happily until Jim comes with scissors and removes that reaction force, and now Dwight falls down to the ground. All right, so here I want you to give this a try. I want you to figure out the interaction pair, the action force, the reaction force, and the result for each of the following two scenarios. So here's the first scenario. Michael hugs Jim. So at that moment when Michael hugs Jim, what are the interaction pair, the action force, the reaction force, and the result? Take a minute and think through this. All right, so let's talk through this example together then. The interaction pair would be Michael and Jim, right? Those are the two objects that are interacting here. Okay, the action force might be Michael hits Jim. You can see it's a rather, I mean, this video is kind of slowed down, but it's a rather forceful hug. He like literally knocks him sideways. So action force, Michael hits Jim. Reaction force, Jim's body hits Michael. And then the result is that Michael shows his affection. I don't know. Whatever you think the result is, Jim goes flying sideways, all that jazz. Okay, here's another example. Dwight throws a watermelon off of the roof. So take a second, think through this example, identify an interaction pair, an action force, a reaction force, and a result for this scenario. And I will say there are multiple ones that you could choose. So try to think through one or a couple, and we'll come back together and talk about it in just a moment. All right, let's talk about it. So again, there are a couple of examples that you could choose. You could choose the interaction pair being the watermelon and the earth, right? So in that case, the earth is pulling down on the watermelon. And actually, the watermelon, since it has mass, it also has gravity, it's pulling slightly up on the earth as well. Same amount of force. But of course, since the watermelon is much smaller, much less massive than the earth, it has less inertia, so its motion is easier to change than the Earth's motion. They're pulling on each other with the same amount of force, so the force that the Earth is pulling down on the watermelon exactly equals the force that the watermelon is pulling up on the Earth. But back to our example of the bug hitting the windshield, it's much easier to change the motion of one of those objects. And in this case, it's the watermelon. So that could be an interaction pair. Action force, reaction force, and the result would be the watermelon falls down. Okay, another interaction pair that you could choose would be the watermelon and the trampoline. So action force, watermelon hits trampoline. Reaction force, trampoline applies force to watermelon. And then the result for that is that the watermelon catapults upward. Another interaction pair could be the watermelon and the car. So watermelon hits car kind of hits watermelon back. The watermelon is not strong enough to withstand that force, and so it splatters. Okay. All right, so Newton's second law is also known as the law of force and acceleration. So this is the one that we're typically used to, like plug and chug in equations. Like this is the one we see a lot in mathematical scenarios. But as we saw, the other two laws do have equations associated with them as well. But here we go, the second law. The acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Excuse me. So inversely proportional means that two variables affect each other in opposite ways. So if we increase the mass, we decrease the acceleration. Directly proportional means they affect each other in the same way. So if we increase the force, we increase the acceleration, right? So basically what this law tells us is that the more mass an object has, the more force it requires to change its motion. And so phrasing it in that way, you can really see how this law is connected to both the first law and the third law. Um, but again, changing its motion is the key thing here. Change the motion. So the ways that we'll see this written are either acceleration equals net force over mass, or you might see F equals ma, net force equals mass times acceleration, or the sum of the forces equals mass times acceleration. So when we see it written in this way with the sum of the forces, we really have to be careful to remember that forces are vectors and the direction matters, right? So if we have a force that's pushing backwards or pushing down, those would be added as negative numbers in our sum, okay? And also, we're not going to really add vertical forces with horizontal forces because, as we learned in chapter 3, horizontal motion and vertical motion are not connected to each other, they're independent. So when we use these any of these equations, we really have to be careful about what exactly it is that we're adding together, which directions we're considering. We have to keep things separate, etc. We'll get into that starting tomorrow when we go through some of these example scenarios. But anyway, this is the 3 of the different ways that you might see this law written. So just a conceptual example here. You and your friend are racing shopping carts at the store. Yours has a mass of 10 kilograms and your friend's is 20 kilograms. So if you guys are pushing with the same force, whose shopping cart will go faster? Well, um, I am just going to write it in terms of this kind of simplified equation. Um, and I'm representing the magnitudes of these numbers by relative sizes. So if you guys are pushing with the same force, the force is the same size, and one of the carts has a smaller mass than the other one, in order to have the same force, one of the carts is going to have a much bigger acceleration, right? A small times a big equals a medium, and a small times a big equals a medium. So the cart with the less mass is going to have a higher acceleration in order to equal the same force. Okay. Similarly, if you guys are neck and neck, so if nobody's winning, if you're tied, who is pushing harder? Well, in this case, your accelerations are the same size. And again, one cart is half the mass of the other one. So if you have a small number times a medium number, you get kind of a medium force. If you have a big number times a medium, you get a big force, right? So it takes a lot more force to push a heavier cart faster than it would to take to push a lighter cart. Okay. Hopefully that makes a little bit of conceptual sense. Okay. So here are the most common forces that we'll use in Physics 1. So I'm going to tell you their name, their symbol, so how you'd see it written in an equation, what it means, which direction it acts, if it's a contact or a field force, and an equation that we might use to calculate it. So again, this might not be all of the forces that you will use. This is definitely not all of the forces that exist, but these are the most common ones that you'll see appear in homework problems and test problems. First of all, gravity, also known as weight. So the symbol for this force could be a capital W, meaning weight. It could be F sub G, F sub grav, something along those lines. And so this force is due to the gravitational attraction between two objects. Now, any objects that have mass have a force of gravity associated with them. Not just the Earth and not just like things as large as planets and stars, but everything. I have mass, so I have a force of gravity. I am gravitationally attracting things to myself right now. but I'm really close to the Earth, and the Earth has more mass, so it has more force of gravity. And so my force of attraction is not nearly as strong as the Earth's force of attraction. Shucks. It's all right. I'm already married. Don't worry about it. So everything that has mass has that force of gravitational attraction. And the direction of that, since typically we're talking about problems on Earth, is straight down towards the center of Earth, but really it's towards the center of whichever object you're talking about. So towards the center of me, or towards the center of the sun, whichever the object is, the direction of gravity is towards the center. Like we said already, this is a field force, so you don't have to be touching the Earth or touching the object in order for it to still have a gravitational pull on you. And the way that we calculate the force of gravity is mass times the acceleration due to gravity, which g on Earth, remember, is 9.8 meters per second squared. It's different for different planets, different for different objects, but since, again, usually we'll be talking about the force of gravity due to Earth, we're going to use 9.8. Another common force is called the normal force, also known as the support force. So we can see this written as capital N, although that's confusing because remember the unit of force is newtons, which is the capital N. So typically people don't use capital N to mean normal force. They either use F sub N or F norm. And this is the kind of force that is exerted by a surface onto an object. So again, if we have a book sitting on a table, for example, the table is the surface that's holding up the book. So the table is exerting a normal force onto the book. But if I'm like leaning my hand against the wall or something, then the wall is the surface that is holding me up. And so the normal force is actually out of the wall. And the direction of it would be perpendicular and away from the surface. So if we're having a table, the normal force would be pointed up, perpendicular to the table. If we're talking about a wall, then the normal force is pointed out from the wall, because normal actually means perpendicular. That's how it got its name, as the normal force. So this is a contact force because in order for something to be supporting an object, it has to be touching it. And usually the normal force is equal to the weight. Again, because like we talked about this with the soccer ball sitting on the ground, if the normal force were more than the weight, then it would launch the soccer ball into the air. And if the weight were more than the normal force, then the ground wouldn't be giving enough force to support the ball, and the ball would fall right through the ground. So usually it's equal to the weight, unless we have a problem where something is on a ramp or some other kind of angle. And then we'll need to calculate it using some trigonometry. Friction, another common force. Usually we'll see this written as a lowercase f, or F sub F, force of friction, or F fric. And so this is the kind of force that opposes the sliding motion between two surfaces, right? So when you rub your hands together, you're creating friction because two objects are sliding against each other. So the direction of friction is parallel to the surface, but opposite the direction that it's sliding because it opposes the motion. So if your object is sliding to the left, then friction will point to the right. If your object is sliding to the right, then friction will point to the left. Okay, this is a contact force because objects need to be touching each other in order to slide against each other. And I think this is the most fun equation in all of physics. Because the force of friction equals this coefficient, mu, coefficient of friction, which tells us how slippery the surface is, times the normal force. Right, so this coefficient of friction, we'll talk about it a little bit more when we get into friction in more detail, but it's a number usually between 0 and 1, like a decimal between 0 and 1. The closer it is to 0, the more slippery the surface is. Okay. And you can look up these tables of these coefficients. For any two materials rubbing against each other, that will determine the coefficient of friction. It's different if you have like wet rubber on asphalt versus dry rubber on asphalt, which is why it's easier to skid out when you're driving on a wet road. So all of these things come into play with this coefficient of friction. Tension is another common one. We see that written as capital T or FT, F10s. And so we'll have tension whenever we're dealing with something being pulled by a rope or held up by a wire or a string, something like that, that's attached to the object. So the direction of tension is away from the object and parallel to the rope. This is a contact force because the rope has to be connected to the object in order to pull on it. And there's not really an equation that we use for this. Most likely, either we'll have to find it based on the scenario, or it will be given to us in the scenario. And we'll see lots of examples of that tomorrow and next week. Air resistance is another less common one, but you might see it in Physics 1 a little bit. We usually see that written as FD for drag or F air for air resistance. And this is a kind of frictional force, but specifically due to wind. So again, this opposes the direction that something is moving. It's a contact force, and there's not an equation that we'll use for it in Physics 1. There are equations that you can use for drag, but that would be more in terms of like fluid mechanics and other classes that you won't get into in Physics 1. There's an applied force, FA, and so this would be any other force that's given to you in the scenario that's not like specifically one of these other things. So of course that would be based on the scenario, which direction it's pointing. And there's no real equation for it because it would be based on the scenario. So that might be like if I push a ball down the stairs. Well, a push isn't necessarily any of those forces, but it is a force. So we would call that an applied force in this scenario. And then lastly, we have net force, which again isn't a force that you would necessarily like label on your object, but it is important for our mathematical purposes. So a net force is the sum of all of the forces added together, considering their direction. So that's what it means when it says a vector sum. That means we're remembering that forces are vectors and the direction matters. And so the net force is going to be pointed in whichever direction is unbalanced. And so we'll get into more detail about that just really quickly right now. So a net force, the vector sum of all forces, or the result of adding up all of the forces acting on an object according to their directions. So the way that I liked to phrase it was that it's whatever amount of unbalanced force is kind of left over. So for example, if you are playing tug of war with your friend, your team pulls to the right with 100 newtons of force. The other team pulls to the left with 60 newtons of force. Which team is going to win and by how much? Well, we kind of instinctively know like the team that's pulling harder is going to win, and they're going to win by 40 newtons. That's the difference. That's the unbalanced force. So 40 newtons to the right is that force that's like left over, that unbalanced force. That's the net force. So if the net force on an object is 0, then all of the forces are balanced. Your two teams are pulling equally, and the object is in equilibrium. It's not moving. Its motion is not changing, I should say. Motion is not changing. So left would equal right, up would equal down, but we can't necessarily say that left equals up, for example, because we don't really compare horizontal with vertical, right? We compare horizontal with horizontal and vertical with vertical, right? So that's what we mean by the forces are balanced, right? We're considering up versus down and separately left versus right. So this could happen if an object is at rest or moving at a constant velocity, right? The net force is 0, the motion does not change. This happens at rest or when it's moving at a constant velocity in a constant direction. So these unbalanced forces, or these net forces, non-zero net forces, are what cause the change in the motion of an object or an acceleration. All right. Do you guys have any questions today? That was a pretty quick overview of all of Newton's 3 laws of motion. And again, tomorrow we'll start applying them in different scenarios. Can I show the table of forces one more time? Yes, I can. There you go. Yes, so we'll start applying all of these things that we just talked about. But again, hopefully you guys were at least introduced to some of these concepts, in high school, even middle school for some people. And now we'll just kind of flesh it out a little bit more. All right, well, if you guys don't have any questions, I will see you all tomorrow, and I hope you guys have a great day.